Hello students, welcome to EPG Pathshala. I am Dr. Javed Ali from Department of Pharmaceutics, School of Pharmaceutical Education and Research, Jamia Ahmedabad. Today we are going to discuss about a module titled as Non-Linear Pharmacokinetics under the paper Biopharmaceutics and Pharmacokinetics. In the present module, we are going to introduce the term non-linear pharmacokinetics, what its relevance means to us, the ADME processes which are involved in non-linear pharmacokinetics, the Michael-Menten equation which is used to describe non-linear pharmacokinetics as such, what are the causes of these non-linearity and how it is being detected in terms of saturation mechanism. Coming to the introduction of pharmacokinetics, the kinetics of a pharmacokinetic process in some instances may change from primarily first order to primarily zero order with the increase in dose. In case of linear pharmacokinetics, generally the assumption is that you follow first order pharmacokinetics. Sometimes a mixture of both the reaction is seen and hence they are said to have followed mixed order kinetics. As the deviation is seen from the original linear pharmacokinetics, the rate process of such drugs is called as non-linear kinetics. They are also known as dose-dependent pharmacokinetics, and the form pharmacokinetics non-linearity are given in figure 1 as shown. In the present figure, the various causes of pharmacokinetic non-linearity is being mentioned, where ADME process are being described in terms of drug absorption, drug distribution, drug metabolism, and drug excretion. In the coming slides, we are going to talk how these four processes are related to non-linear pharmacokinetics. There are many other ways to determine the non-linear pharmacokinetics parameters, and the easy ways are at different doses to examine steady state concentration when there is non-linearity. Direct proportionality of steady state concentrations with dose is not available, or else there is no existence of such proportionality is present. There may be pharmacokinetic parameters such as amount of fractional bioavailability, half-life elimination, or total systemic clearance at other doses amount of drug. Further changing in these constant parameters will lead to non-linearity. Now coming to ADME process, non-linear observed parameters are being discussed as non-linearity can be seen in drug absorption, drug distribution, drug metabolism, and drug excretion. Drug absorption, this is a process by which the drug remains unchanged from the site of administration to that of its systemic absorption, and its effectiveness is determined by its concentration of the similar drug that is ingested at the site of action, where its amount quantitatively measured in the plasma. Most importantly, rapid absorption of drug leads to therapeutic level to reach and to showcase its pharmacological effects. Mechanisms of drug absorption which plays an important role in the kinetics are its transportation, either passive or active. They can be either categorized into intracellular, intercellular, or vesicular processes. Some processes require energy for transportation of drug from one layer to other bilayer. In some carriers, they are carrier bound, binded reversibly or non-reversibly with solute molecules. And mainly these carrier bound are capacity limited. Once as higher the concentration of drug, then the system shows saturation. The drug absorption increases linearly to some extent, and later when carriers get saturated, then it becomes curvilinear and later gives a constant value at higher doses and give non-linear kinetics. At such cases, as increasing the dose, the bioavailability of the drug gets decreased, and there are different ways that take places are: number one, in case absorption is solubility or dissolution rate limited. In some drugs at higher doses, saturation solution of the drug is formed in the gastrointestinal tract and other sites and furthermore, the rate of absorption value remain or it reaches constant. In second case, carrier mediate transport system, in some vitamin saturation of transport system at higher doses give non-linearity in the equations. In others, liver metabolism or gut wall of pre-systematic shows saturation, that is, the saturation of few drugs at high doses mainly leads to increased bioavailability. Certain factors mostly affected are area under curve, which is being termed as AUC, Ka, that is the absorption rate constant, and the Cmax, that is the maximum concentration at Tmax. Mostly these cases affect above situations in decreasing order and increase in the third case. Non-linear drug absorption is less seen where bioavailability is affected in maximum amount. Now coming to drug distribution, the process that defines the drug gets distributed among the sites of body. In the coming figure, we are going to see how the drugs are being distributed. Certain step process followed in distribution are permeation of bound and unbound drug and permeation of amount of drug that is distributed. Mainly, the other parameter which affects such distribution are as follows. Number one is the binding of tissues of metabolites, mainly depending over size of drug. And the size of drug means to us as the molecular weight. Organ and tissue dimensions and its diffusion ratio, tissue compartments, and other factors which are miscellaneous types like age, diet, and other drug complications. Barriers have a structural difference which have number of barriers like simple endothelial membrane, there may be simple cell membrane, there may be blood-brain membrane which is also being referred to as BBB, blood-brain barrier, blood CSF membrane, that is the cerebrospinal fluid membrane, blood placental membrane, and the plasma protein bindings. It also refers to the cell protein binding and external binding, vice versa. Kinetics of protein bind drug formulated on the basis of law mass of action, which show mainly forward action. The figure shown on the screen describes binding of drugs with blood proteins. The variety of plasma proteins are available, like human serum albumin, which is generally get bound to large variety of drugs. The alpha acid glycoprotein, these binds mainly to the basic types of drugs, weekly basic drugs. Lipoproteins, which are generally bound to lipid-loving drugs because both are lipophilic in nature. Alpha globulins, which generally bound to the steroidal drugs, and hemoglobin, which is mainly a blood product and generally rarely binds. Non-linear kinetics in case of drug distribution at higher doses is because of plasma protein sites for binding to acquire saturation. Drugs such as non-steroidal anti-inflammatory drugs have finite number of sites of attachment. As the concentration increases, so as the unbound fraction of drug is also increased. Tissue binding sites to acquire saturation, mainly anesthetics with single large doses or repeated dosing can also cause saturation of tissue binding sites. Main parameter in this case are volume of distribution and clearance, as the volume of distribution relates to the kinetics as unbound clearance of drugs causes accumulation and increase in response. Drug metabolism, the process of irreversible change from one state to other, is being referred to as metabolism. Metabolism of drugs are being discussed as for highly lipophilic drugs as accumulation plus phase 1 activation plus phase 2 activation, which leads to final excretion. For lipophilic drugs, phase 1 activation plus phase 2 activation leading to excretion or elimination of drugs. Polar drugs undergo phase 2 activation leading to excretion of drug, and water soluble drugs undergo direct excretion without undergoing phase 1 or phase 2 activation. The table depicts the chemical pathways of drug metabolism. Phase 1 reactions leads to increase in the water solubility and hence new attachment substrate like hydroxyl, carboxylic, ammonium and SH they bind to the drugs and it is a asynthetic type reaction. Whereas phase 2 reactions, they are mainly conjugation occurring reactions and they are also known as synthetic formation of reactions and synthetic type reactions. Large changes in plasma concentration at steady state generally examined in small administration of doses as mostly non-linear kinetics are depending upon capacity. Reasons for such metabolism are given in the next figure where metabolism saturation occurred due to enzyme or cofactor or increment of effect due to enzyme binding, enzyme induction in some cases, which refers to metabolism saturation due to dose and time dependency. In some cases, less plasma concentration is achieved on increasing frequency of administration. Other reasons for such saturation can be biotransformation by binding within the sites, enzyme induction, and other bodily issues. The figure on the slide shows the factor regarding metabolism and biotransformation of drugs. The metabolism or biotransformation of drug is dependent upon the physicochemical factors which are mainly stereochemical metabolite etc., lipophilicity, dissolution behavior and other related factors. It may be chemical factors where induction of enzyme or inhibition of enzymes takes place and biological factors which include the species specific like age, food and other differences. Excretion, it is a process that the drug property gets changed from one form to other. It is the irreversible change that metabolites are cleared from inside body to excretion. Excretion relates not only to the kidneys but also to non-renal excretion such as biliary, lungs, skin, saliva, etc. Excretion through renal, it employs three basic mechanisms. The first is the glomerular filtration, where filtration of water and other drugs and other metabolites take place, mainly non-selective. Anionic compounds are easily filtered in glomerulus as it acts negatively charged. Glomerulus filters 1.5 liters of urine per day. The second mechanism, the tubular secretion, is mainly absorption of acidic and basic drugs took place and are unaffected from pH and any protein binding. Tubular reabsorption is a process after GFR, that is the glomerulus filtration rate, and goes parallel with that of tubular secretion. As this process is further divided among two active and passive process. Active process relates to essential elements to be absorbed in the body as electrolyte, glucose, vitamins, etc., and they are known as nutrients of body that are important for the chemical balance inside the drugs. Passive process refers mainly to the xenobiotics, which are our drugs, and lipophilic absorption of drugs are the examples of such where rate of excretion is equal to the rate of filtration plus rate of secretion minus the rate of reabsorption. The present table discusses the excretion sites of different types of drugs, the site of excretion and the corresponding types of drugs which are excreted. Under glomerular filtration, the drugs which are being excreted are water and unbinded xenobiotics, that is, they are unbound plasma protein drugs. Tubular absorption, acidic and basic compounds and their byproducts. Tubular reabsorption, acidic and basic compounds and other lipid-soluble drugs as well. Other non-renal excretions like biliary excretion, bile productions through cell lining are active process. When it is active process, it is capacity limited, saturable process, and very less amount of drugs falls on this category. Accordingly, molecular weight of 300 Daltons are mainly excreted through urine, and 300 to 500 Daltons are mainly excreted through bile. Different factors that affects biliary excretion are the molecular weight, biotransformation, and other miscellaneous factors like diet, age, and gender, etc. Lung excretion is another non-renal mechanism where anesthetics are absorbed through such diffusion process. Saliva excretion, it shows passive process on basis of pH. Mainly the pH ranges from 5.8 to 8.4. Some drugs shows same excretion like enterohepatic cycling. Skin excretion, it is also passive process which is based on pH. Mainly the drugs and their other bioproducts are excreted by sweat. Main important process, the renal clearance of drugs that already gets fully saturated depends upon the secretion of active tubular, that is mainly antibiotics and other drugs. Also, as they get saturated, then the clearance of renal decreases. Tubular reabsorption, some of the water soluble after saturation, the renal clearance increases. When a specific pharmacokinetic process engrosses the presence of carriers, they are substrate specific and have definite capacities and also can get saturated at high drug concentrations and shows the non-linearity phenomena. The kinetics of such capacity limited processes can be explained by the Michaelis-Menten equation. Coming to Michaelis-Menten equation, if metabolism is the only pathway of elimination, the rate of metabolism or elimination is defined by the Michaelis-Menten equation, where the rate of change of concentration is equal to Vmax into C upon Km plus C. Here Km reflects the Michaelis-Menten constant and not the rate constant for metabolism. The Vmax describes the maximum rate of metabolism and Km as defined earlier is a Michaelis-Menten constant and C corresponds to the drug concentration. Vmax is dependent on the amount or concentration of enzyme which is available for metabolism of the drug. Km is the concentration of the drug that results in a metabolic rate equal to 1/2 of Vmax. That is, the Km, that is the Michaelis-Menten constant, is equal to Vmax divided by 2. Also, Km is inversely correlated to the affinity of the drug for the metabolizing enzymes. The unit for Vmax is a unit of elimination rate and is normally expressed as amount per unit time, that is milligram per hour. However, in some instances, it may be expressed as concentration per unit time, that is milligram per liter per hour. The equation here explains the relationship between Vmax and C. However, different regions of Michaelis-Menten curves, which is shown in the figure, can be examined with regard to drug concentrations. The figure depicts the typical Michaelis-Menten curve, which shows reaction rate on the y-axis and the corresponding concentration of the substrate on the x-axis. The Vm is interpolated from the curve when the value of half Vmax is being calculated. Michaelis-Menten equation is generally used to explain the kinetics of in vitro, few enzyme catalyzed in vivo and in situ processes. When the concentrations are low, that is, the Michaelis-Menten constant is greater than C, then Km plus C is approximately equal to Km, and thus the Michaelis-Menten equation reduces to minus dC over dt equals to Vmax into C over Km, where Km plus C has been replaced by Km because C is lesser than Km. Because both Vmax and Km are constants, the metabolism rate is proportional to the drug concentration and is constant. That is, first order process, which is similar to a linear pharmacokinetic reaction. When the concentrations are high, that is C is much greater than Km, then the same equation, the denominator changes to C. That is, dC by dt is equal to Vmax into C divided by C, or alternatively dC by dt is equal to Vmax. And hence this equation in the reduced forms follow zero order kinetics. Therefore, it can be concluded that at high plasma concentration, first order kinetics are not seen, which is generally replaced by a zero order kinetics at high concentration. When given in therapeutic doses, most drugs produce plasma drug concentrations which are well below the Km for all carrier mediated enzyme systems, that is, active processes affecting the pharmacokinetics of the drug. Hence, most of the drugs at normal therapeutic concentrations follow first order rate processes. Some of the drugs like phenytoin and salicylate saturate the hepatic mixed function oxidases, that is cytochrome P450 system, at higher therapeutic doses. With these drugs, elimination kinetics is first order at low doses and mixed at high doses, and shows zero order at very high therapeutic doses. If a single IV, that is intravenous bolus injection of drug, is given at a dose level of D0 at time T0, the drug concentration, that is the CT in the plasma at any time T, can be calculated by an integrated form of Michaelis-Menten equation. That is, C0 minus Ct divided by T will give you Vmax minus Km into C over T, natural ln of the ratio of initial concentration with time, where C0 is a concentration at time T equal to 0. Alternatively, the amount of drug in the body after an IV bolus injection may be calculated by the relationship of D0 minus dt divided by T equal to Vmax minus Kmc over T, and natural ln of dose at time T equal to 0 divided by dose at time T, where D0, which is the amount of drug in the body at time T equal to 0. This equation can be used to study the decline of the drug in the body after administration of different therapeutic doses. Here, the Km and Vmax of the drugs are unknown. By rearranging the equation with time to decline, a certain amount of dose of a drug can be calculated by the following equation, that is T equal to 1 over Vmax into D0 minus dt plus Km natural ln of dose at time T equal to 0 divided by dose at time T. This equation explains an inverse relationship between the time for the dose to decline to a certain amount of drug in the body and Vmax. Actually, Km can be set as a hybrid constant in enzyme kinetics that may represent both forward as well as backward reactions. It is equivalent to the concentration of the drug in the body at Vmax divided by 2. The one compartment open model having capacity limited elimination pharmacokinetics effectively explain the plasma drug concentration time profile for a number of drugs. Estimating Km and Vmax, it is being estimated by various methods. The method 1 talks about using the equation which gives the relationship of drug biotransformation to the concentration of the drug in the body. When an experiment is performed by using different concentrations of the drug C, a series of reaction rates V may be calculated for each concentration. Vm and Vmax can be determined by using these special plots. Now coming to the equation, that is V equal to Vmax C over Km plus C, and rearranging the equation, that is the reciprocal terms of the equation leads to 1 over V equal to Km over Vmax into 1 over C plus 1 over Vmax. And then this equation gives a linear equation when 1 over V is plotted against 1 over C. The resultant intercept for the line is 1 over Vmax and the slope is Vm divided by Vmax. The plot here shows the 1 over V on y-axis and 1 over C on the x-axis. The straight line gives slope and intercept, where slope is given by Km over Vmax and the intercept relates to 1 over Vmax. In the method 2, again if we are rearranging the original equation, we get Cv equal to 1 over Vmax C plus Km over Vmax, and plotting Cv against T yields a straight line giving 1 over Vmax as a slope and the intercept as Km over Vmax. The C over V on y-axis and a C on x-axis give a straight line and the slope giving the 1 over Vmax and the intercept giving Km over Vmax. In another method, we can also again arrange the equation as V equal to minus Km V over C plus Vmax, and a graph where reaction rate is being plotted on the y-axis against V over C on the x-axis gives a straight line where slope gives minus Km and the intercept shows Vmax. Method 2 and 3 gives a better result as the data is more spread out. When the data is more scattered, one method may be more accurate than the other. Simply, a graph can be plotted on the basis of the data provided, which can be further used to examine the linearity of the graph. Now coming to causes of non-linearity. Non-linearity may occur by one of the following factors. These factors we have already seen in the initial slides, where drug absorption, distribution, metabolism, and excretion plays an important role. In drug absorption, non-linearity may arise when absorption is solubility or dissolution rate limited. When absorption involves carrier-mediated transport systems. When pre-systemic gut wall or hepatic metabolism attains saturation. So these are all interrelated factors which are related to absorption, which is actively absorbed, carrier mediated and saturable. Coming to drug distribution, in drug distribution, non-linearity may arise due to saturation of binding sites on plasma proteins. There is a specific number of binding sites for a particular drug on plasma proteins. Therefore, as the concentration of the drug is raised, simultaneously unbound fraction will be raised. Saturation of tissue binding sites. Saturation of tissue storage sites may occur due to multiple dosing or with a large single bolus dose. Due to the unavailability of the binding sites, free plasma concentration increases in both the above mentioned scenarios. However, volume of distribution increases in the first scenario, whereas it decreases in the second one. In addition, clearance is also affected depending upon the extraction ratio, and it increases with the increase in the saturation of the binding sites. Coming to drug metabolism, capacity limited metabolism is clinically most important in non-linear kinetics, as the minute change in the administered dose can produce large variations in plasma concentration at steady state. The non-linearity in metabolism of drug is due to capacity limited metabolism due to enzyme or cofactor saturation. It may be due to enzyme induction on repetitive administration over a period of time. A decrease in peak plasma concentration is observed. The fourth process, the drug excretion. In these two saturable active process in renal excretion of drugs are involved. The active tubular secretion. As the carrier system is saturated, a decrease in renal clearance is seen. In case of active tubular reabsorption, as the carrier system is saturated, an increase in renal clearance is seen. Detection of non-linearity. The simplest methods to detect non-linearity are: number one, determining the steady state plasma concentration at different doses. Linearity of the kinetics exists when the steady state concentrations are directly proportional to the dose. When there is non-linearity, such proportionality is not seen. Determining the important pharmacokinetic parameters like fraction bioavailable, elimination half-life, total systemic clearance, etc. at different doses of the drug. Any change in these parameters indicate the non-linearity as they are generally constant. Coming to saturation mechanism, this mechanism is also known as capacity limited metabolism. The enzyme metabolism process of drugs may be depicted by a simple equation where an enzyme reacts with a substrate to form a enzyme substrate complex, which ultimately leads to enzyme plus a metabolite. Firstly, there is an interaction between the subsaturated enzyme producing an intermediate which is known as substrate enzyme intermediate. This intermediate complex with the release of enzyme is further processed to produce a metabolite. The enzyme which it releases is used again to react with more substrate molecule. As per the Michaelis-Menten equation, at very low substrate concentration, the availability of enzyme is much greater than the presence of substrate molecules. Hence, when the concentration of the substrate is increased, the rate of metabolism is also increased. Although, after a certain point, when the plasma concentration increases, the increase in the metabolism rate is less. Alternatively, when the concentration of the substrate is very high, according to the concentration of the available enzymes, the enzyme molecules get saturated with the substrate, and on further increasing the concentration, the rate of metabolism will not change, that is, Vmax has already been attained. When the metabolism is the only pathway of elimination, then rate of metabolism is given by Michaelis-Menten equation. The equation we have already seen, that is the metabolism rate is equal to Vmax C upon Km plus C. Vmax directly depends on the concentration of the enzyme available for the metabolism of drug, and Km is a concentration of the drug that results in a metabolic rate equal to 1/2 of Vmax. Additionally, Km is inversely proportional to the affinity of the substrate for the metabolizing enzyme, that is, higher the affinity, lower the Km value. The relationship between the rate of metabolism and concentration is already given by the equation, that is metabolism rate equal to Vmax C over Km plus C. When the concentration of the substrate is much lesser than the Km, then this concentration term may be eliminated from the denominator of equation, which gives the equation as metabolism rate equal to Vmax C plus Km. As both Vmax and Km are constant terms, the metabolism rate is directly proportional to the substrate concentration and a constant, and hence metabolism rate equal to K into C, where K, the constant, is equal to Vmax by Km. The units of K are milligram per liter per hour, and the equation is similar to the standard first order rate equation. When the concentration of substrate is much higher, then Km may be deleted from the denominator, and hence metabolism rate is equal to Vmax. This reduced equation is similar to the standard zero order equation, and this equation explains when the substrate concentration is much higher than Km. The rate of metabolism is a constant, that is Vmax. There are several complications regarding Km and Cmax theoretically in one compartment system, that is capacity limited process. Km and Cmax will be larger when drug excreted by any other capacity limited process, parallel flow of capacity process with that of first order kinetics. Drugs behaving in non-linear way within its therapeutic range, resulting in lesser usage and more accumulation rate. In conclusion, students, we have introduced the topic on non-linear pharmacokinetics, and we have seen that the four processes: absorption, distribution, metabolism, and excretion, how they are interrelated to non-linear pharmacokinetics. The best suited equation, that is the Michaelis-Menten equation, how it takes part in finalizing the non-linearity of pharmacokinetic reaction is being discussed. The causes of non-linear pharmacokinetics have also been discussed with you, and how to detect the non-linearity pharmacokinetic mechanism. Thank you.